Well, the first talk this morning will be by Dave Evans, entitled Some Consequences Upon the Auroral Electron Population of a Magnetic Field Aligned Potential Difference.
Well, I'd like to discuss for just a little while an old chestnut of an auroral acceleration mechanism, which is just letting the low-energy electrons drop through a potential drop along a magnetic field line and squirt into the atmosphere to produce auroras. This sort of picture is continually discredited, and it continually resurfaces again to explain data. The first slide sort of shows the general geometry that I'd like to adopt and discuss. That is, you assume that there's a region removed from the atmosphere where there's a potential drop along the field line. You shovel hot plasma in the top, and this plasma could be a Maxwellian velocity distribution characterized by a temperature and a number density. The plasma is just assumed to be accelerated freely through that potential drop, and it squirts out the bottom here in a very highly collimated beam, which has two major characteristics. There should be no particles of high pitch angles, large pitch angles, that's near 90 degrees, and there should be no electrons of low energies because everything is assumed to have fallen through the potential drop V. Well, unfortunately, in the observations of auroral precipitation, there are significant fluxes of particles having both high pitch angles and low energies. And these fluxes are so significant that you really can't dismiss them out of hand as being spurious or some black magic process. Well, I mulled about it for a while, and after 6 months or so, I realized the obvious, really, and that is that this highly collimated jet of electrons may go right on down to the atmosphere and produce the aurora, but it also produces a copious number of upgoing low-energy electrons. These are both backscattered primaries and also secondary electrons. These electrons will float up the field line, and they'll hit this potential hill, which I've put there to produce the primary beam. They'll turn around and come back down again, so that if your rocket was in this intervening region between the electric field and the atmosphere, measuring precipitating particles, you should measure both the primary beam and a large population of particles which originated from the atmosphere. And the idea was, could the forbidden particles, the high pitch angle and the low energy particles, could these particles be explained on the basis of backscatter from the atmosphere? So the problem I addressed myself to was, in fact, trying to model what the beam or the total electron population would look like in this intervening region. The primary beam was modeled in just the fashion I described. You allow a Maxwellian plasma to diffuse across this boundary and be freely accelerated downwards to produce the beam jet. The backscatter of electrons from the atmosphere, I didn't really model. I developed a computer mnemonic, I don't think you can call it any more than that, using the theoretical results in the recent paper by Banks, Chappell, and Nagy as a guide. I don't pretend that the mnemonic I developed, which basically calculates a backscatter and secondary electron spectra as a function of primary electrons, primary incident electrons, I don't pretend that it's a particularly accurate one, but I certainly feel that the fluxes it returns are valid to within an order of magnitude, and I think for a numerical calculation, just to see whether this general effect could be of any importance or not, I think that that's adequate. The next slide shows, for the benefit of people who are familiar with backscatter, the backscattered and I should call it the upgoing flux spectrum, which my computer program computes as a function of 4 representative incident electron energies. And these 4 curves ought to allow people in the audience to judge whether the mnemonic is wildly inaccurate or whether it's a fairly accurate representation. The backscatter population, or the upgoing flux population, is made up of 2 components. One is this secondary electron component here, whose general spectral shape is almost invariant. It's almost independent of the incident particle's energy. It's just a secondary electron population such as you'd get off a surface or a phototube dynode. These higher energy particles here are the primary particles which have been rattled around in the atmosphere and come back out of the atmosphere with a various reduction of energy. The vertical scale there is in omnidirectional flux. That's electrons per centimeter square per second per eV, per incident primary electron. Well, I use curves like this and make the big jump to the assuming that the curve is valid independent of the incident angle of the particle, and that the backscattered population is isotropic, so I can convert these omnidirectional fluxes to directional fluxes. I'm not really willing to defend the mnemonic too much, except in the context that it probably gives results which are accurate to within a factor of 5. Well, I went and tried to model then the total electron population in this intervening region. And these are the results for a model which assumed that the parallel potential drop was located at about 1,500 kilometers above the Earth, so that there was a factor of 2 change in the magnetic field intensity between the accelerator and the atmosphere. I assumed that the Maxwellian hot plasma that I was using as a fuel for the accelerator was characterized by an 800 electron volt temperature and a density of 1.5, which are not outrageous figures for plasma sheet populations, for example. I allowed this Maxwellian to fall through a 2,000 volt potential, go into the atmosphere, and then I tried to calculate the total backscatter population that would be produced, taking into account granddaughters as well. That is, backscattered particles which go up, are reflected, come down again, and produce still more backscatter. So there's a cascading process involved here. This is the total electron directional energy spectrum that I computed for 0-degree pitch angle. The discontinuity here separates those electrons which have originated from the atmosphere from those electrons which are truly members of this primary beam that have been accelerated by the electric field. I point out that a detector trying to measure such a spectra would smooth out that infinite gradient, and it would look just like a bump. Now, and with that in mind, I'd like to point out that in fact this electron energy spectra looks very much like the sort of energy spectra that are in truth observed above auroral forms. I'll discuss some of the features. The large peak intensity here at 2,000 volts is associated with the potential drop I assumed, of course. The slope of the higher energy portion of the spectra is a measure of the temperature of the plasma that I assumed was fueling the accelerator. These particles exhibit a varying degree of field alignment. These are the primary electron jet. If you were to do a pitch angle distribution at this energy, you'd find the beam was very field aligned indeed. If you were to do a pitch angle distribution at this energy, you'd find that it was modestly field aligned. The collimation cone will have opened up a little bit. To say it another way, if you were to do an energy spectrum at a 45-degree pitch angle instead of 0-degree pitch angle, you would find a peak in the spectrum also, but the peak would be moved out, in this case to about 3 kilovolts. That is, you have a spectrum which is pitch angle dependent, just like Arnoldi showed yesterday. When you go to these electrons, which are in the model are coming from the atmosphere, the pitch angle distribution needn't be field aligned at all. And because I assumed that backscatter was isotropic, the model returns an isotropic flux over this entire energy range. So you're faced with a situation of low energy electrons being isotropic and higher energy electrons perhaps very much field aligned. This rise in the spectrum here is due to all the secondary electron production from the atmosphere. And it's interesting to point out that this spectral shape, this slope here, is almost invariant with the primary electron energy or pitch angle characteristics. It's set by secondary electron emission from gases. The intensity, or just the normalizing factor of that low energy population, is just a measure of the total number of primary particles incident on the atmosphere, not their total energy flux, their total number flux. This is an association that Roger Arnoldi has also obtained in analyzing data. That is that the intensity of these low energy electrons is correlated with the integrated number flux of the high energy electrons incident on the atmosphere. And the association comes out explicitly in this model. I might also point out that because these particles are originating from the atmosphere, the pitch angle distribution is symmetric over 4 pi. That is, if your detector looks down in the atmosphere, they see these particles coming out. And then if you look upwards into this electric field, you see the same particles coming back down at you. And if you were to make the measurement on a rocket, the natural interpretation would be anomalous backscatter, or total reflection of the electrons from the atmosphere, which has been observed time and time again as a characteristic of the lower energy portion of the electron population. As many particles coming out of the atmosphere as are going in the lower energy ranges, and this sort of feature comes out explicitly in the model. Well, I've had such good luck explaining this variety of characteristics that have been observed in the beam that I thought I might try to model a true energy spectrum. And I chose a spectrum that Lew Frank obtained on engine 5. This is a 0-degree pitch angle energy spectrum of electrons in one of these inverted V events. The dots are the measurements, and the solid line here is the electron population that I would compute if I assumed that the initial plasma had an 800 electron volt temperature, a density of 5 per cubic centimeter, and there was a 400 volt potential drop. All these particles from this point down are secondaries from the atmosphere. I think the agreement here is rather good, and I've also tried to model some of Roger Arnoldy's simpler cases with a reasonable degree of success. So this really doesn't prove there's an electric field, but it is encouraging to my mind. Thank you.
How sensitive are your results to the rotation of the potential drop?
Well, when I did the model calculations, I assumed that within the potential drop region, the gradient in the magnetic field makes no difference at all. This simplifies things. Now, with that proviso, what happens if you remove the potential drop to higher and higher altitude, you increase the low energy electron fluxes without changing the high energy fluxes at all. This is because there's a focusing effect of this jetted beam into the atmosphere, and the low energy electron production rate is a function of the omnidirectional rate at which particles enter the atmosphere. And so you increase the omnidirectional rate in the primary beam, you increase the backscatter population. So the net effect is that as you move the accelerating region further and further away, you tend to build up the low energy population in the directional flux frame of reference without changing the higher energy population at all. That's the main effect that I can see.
I just wanted to ask a question about, I presume you're trying to also explain the symmetric tails of the Reasoner and Chappell data on this basis.
I've tried to match that, yeah.
Yeah, I don't quite understand how you get your tails going down from the backscatter. What you're explaining. What you just said that you would see, you get the backscatter tail, and then somehow you would also get the tail going down.
I assume that there's a potential drop above my head, which accelerates electrons downwards. And that means that the auroral electron beam, when it hits the atmosphere, produces backscatter off the atmosphere. These upgoing fluxes don't have the energy to surmount the potential hill that I've assumed is there.
Yeah, but
they're reflected and come back down. Isn't that true?
Well, I don't know. I don't quite understand your model. It seems like you're using electric field to explain both types of acceleration.
Yeah, isn't that nice?
It only points in one direction.
Well, I'm trying to explain the full electron spectra in a consistent fashion with just a simple electric field, and I think there's been a fair degree of success.
Your theory is a one-hemisphere theory.
It's no theory.
No, okay. Your model is a one-hemisphere model. My question is, how do you account for the conjugacy on a fairly detailed scale of auroras?
Well, this is a numerical calculation that just takes an ad hoc assumption and follows my nose. Now, if I were to try to go back to reality, what really may be happening, perhaps the electric field is being produced by one of these current-driven instabilities, and it's the vertical current flow, or the field-aligned current flow, which provides a conjugacy, rather than a common source of energetic particles.
Your computed energy spectra were very convincing. I think you have to be a little more careful on the pitch angle distribution of the backscattered electrons, though. especially as the electric field region gets raised higher and higher in altitude because of the magnetic focusing effect. That is, the backscattered beam will probably be more field aligned at higher altitudes.
Absolutely. I mean, that just falls out of Liouville's theorem.
Right.
But I'm trying to match with rocket measurements, which are generally made at about 250 kilometers, and I'm happy with the agreement at that altitude. But you're right. The low-energy fluxes they have the appearance of becoming field-aligned if you begin to measure them at higher and higher altitudes.
Just a comment on the comment before the present one. The spectra that you fitted from Frank and Ackerson, I believe, was poleward of the trapping boundary. So it's not clear that you want to worry about closed field line type conjugate effects. In fact, we would say that those field lines eventually would thread back into the magnetosheath.
Okay, one last question.
I just wanted to go back to Cole's remark, and applies to this last one too. I think you're modeling this for relatively stable arc type situations, which would be the conjugate type aurora. Isn't that correct? I mean, I think it's a very important point that Cole's brought up here.
Well, this sort of energy spectra that turned out of the numerical calculations is a peak and then a null and then climbing to even higher intensities below 300 electron volts or so. This sort of energy spectrum seems to be associated with discrete auroral forms, and I don't think I ought to characterize it any more
of
detail.
the same type that are found to be conjugate usually, right? I mean,
Well,
simple arcs, things of this nature.
You know, sometimes they're observed in discrete auroral forms which are extremely active, and sometimes in discrete auroral forms which are relatively stable. And I really don't want to characterize the type of aurora beyond the discreteness.
Well, I think that's...
You know, I really don't want to get
You're
hung
not
up
going,
on...
I don't believe you're going to the boundary in this calculation, is what my point is, which Ackerson was...
Well, I don't want to read too much into an agreement between a numerical model and the observation. You know, I don't think logically this ought to prove that there's a parallel potential drop. I think it's a fairly interesting argument. I think it ought to start make one consider the possibility very seriously, but it surely doesn't prove it. Or did it prove it to you?
Eather has a very minute comment.
David, what sort of modification would you expect to the proton spectrum on the same field line?
Lord, I'd hesitate to say. I mean, protons of initial kinetic energies greater than these potential drops ought to be able to penetrate down to the atmosphere, so that the sort of high-altitude proton spectra in a simple-minded picture you'd expect to see just downshifted by the potential drop. The types of auroras where this electron spectra has been seen are the discrete auroras, which are generally unassociated with proton bombardment. So there's really no point of reference in the experimental data to your question.